All right, looks like we are up and running. Hello and welcome back, everyone, to Stat 2602. This is lesson number 9, our very last lesson, and today we're going to be talking about stochastic time series models. So in the last lesson, what we did is we had a time series and we were able to decompose it into its three main components. So we were able to take a time series and break it up into a trend. So what is happening kind of long term? Is things increasing? Is things decreasing? Is it staying relatively the same overall? Is there a seasonality aspect to it? So is there a repetition that happens every single year, every single month, and does it happen year after year? So we need at least 2 years worth of data within a year period. It can't be just at the end of a year. We need within that year as well, but we need at least 2 years to kind of see if that pattern actually exists. So we break it down into trend, we break it down into seasonality, and what we have left is kind of that random error that we were talking about. So we've stripped out trend and seasonality to reveal kind of like a clean signal. But those residuals, the question is, are they truly random? And if they were truly random, we would see no further structure inside of them. But yet, in practice, that noise often carries patterns too that we need to model if we want crisp, reliable forecasts. So today we'll move from the deterministic decomposition, so that is our trend and our seasonality, to reveal that random, that stochastic modeling underneath. Where we treat the remaining structure explicitly, and that's our goal for today. So this is going to be broken up into kind of two parts. We're going to talk a little bit about the theory behind things, kind of explain what we're doing, not focus too much directly onto that, and then we'll go into these models that we're going to help kind of clear up that last little bit, so when we put everything back together, we have one complete picture. All right, so let's get into this. So let's suppose you're the analytic lead at Shopko, an e-commerce retailer. Now, management needs you to have a 12-month revenue forecast to plan inventory, staffing, and marketing. So what we potentially know is there is a steady growth trend, strong November, December seasonality, occasional promos, and we'll say in 2020 there was a supply disruption. Now, what we don't know is if we could model this trend, if we could model this seasonality, we don't know whether the leftover noise has memory, we'll say, that we can use to improve the accuracy. So after we remove the systematic pieces of the time series, so again, that long run trend, that calendar driven seasonality, what remains, again, is that residual, that remainder overall. Now, it would be tempting to call that leftover just random noise and stop there. But again, let's think about this for a minute. In business data, the remainder, after again we remove that trend, we remove that seasonality, rarely behaves like independent coin flips. And what I mean there, this is the complete randomness over it all. Remember, when we're flipping a coin, what happens if I flipped, it landed on a head? Well, the next time around when I flipped that coin again, it didn't matter what happened last time. This is a completely independent flip. So because it landed on heads last time doesn't mean I have a higher probability of tails this time around. I still have that 50% chance of heads, 50% chance of tails. That's it. That is all. But that memory, that leftover last little bit rarely behaves like that. So again, because each coin flip is independent in that sort of sense, we can treat things independently where, again, we don't really care what happened the last time around because it's not affecting this, but that's not the case. So let's suppose we had a strong promotion last month. This could elevate this month's traffic. If we're looking for the amount of hits, if we had a promo last month, it was a big push, that what could have influenced for the following month? Well, more people might be checking out the site, so there might be an increase in that. Now, there might be a supply hiccup one week. That could suppress next week's orders. So in other words, the remainder frequently, I want to say, remembers the recent past. So that memory is what we call autocorrelation. Values that are close in time tend to move together. So again, from one jump to the next, there is some leftover memory that we want to be able to model overall. It's just not independent. It's not like a coin flip, one after the other after the other. One doesn't rely on the last one. Usually there is memory that is carried over from time period to time period that is not captured in the trend, that's not captured in the seasonality, and we need to be able to capture it if we want accurate forecasts. So if the remainder remembers the past, we will fit a model to squeeze out better forecasts. So I did mention it, so let's kind of just talk about this very, very briefly, this autocorrelation. So autocorrelation is, we can think of it as time series memory, the degree to which the period results tends to move with or against recent periods. So 1 month to the next, 1 year to the next. Do the values move together? Is there always an increase in December? Is there always a decrease in January? Things that we can kind of capture along the way that might not have been caught in the seasonality. So if values close in time rise and fall together, autocorrelation is positive. Now, if it's the alternative, one goes up and one goes down, then the autocorrelation is negative. How are these things correlated to one another? So the main tool for diagnosing this structure is the autocorrelation function. We'll define that in just a second. Now, the ACF for short checks memory at different lags. Remember, that's at different points in time. So it could be between now and 1 month, between now and 2 months, so on and so forth. But this does it for all the different lags. So again, checks how long things stay in memory. So for a given lag K, again, a given jump in time by K spots, the ACF reports the correlation between what remains at R sub T and R sub T minus K or plus K, depends on, again, how we're thinking about that shift. And again, this is done across the entire sample space. So large values at small lags, again, when we're talking, say, if things were broken down in months, so it could be between 1 month or 2 months or 3 months. So large values reveal short-term persistence. Seasonal spikes at lags 12 reveal annual echoes that survived and were intentionally left in the remainder. So again, wasn't caught in the seasonality aspect of it. So we will pair the ACF with also the partial autocorrelation. We'll define all of these in just a second, so don't worry about that. We'll get to that point in time. But the partial autocorrelation isolates the direct connection to specific lags after accounting for intermediate lags. So basically what this does is if I look at, lag 1, so jump of 1 month, or lag of 2, jump of 2 months, chances are if I've already calculated for something for the first lag, there's still information that's going to carry over from the first to the second. The partial autocorrelation kind of removes all of the redundant information that we've had previous to that. So it's kind of taking out those echoes from previous lags, we can think of it as. So together with these two summaries tells us whether we want to use certain types of models to, again, account for that randomness overall. So we have an autoregressive model, a moving average model, or we want to combine the two for an autoregressive moving average model. And again, this is all to model the remainder. So we think of kind of the workflow of this big picture. We want to break this down into really 2 steps. So the question becomes, well, how do we turn seasonal trending business data into reliable short-term predictions with honest uncertainty for inventory, staffing, and budgeting? So the core idea is the first thing that we want to do, and we have done in the last lesson, is we want to decompose the time series into its 3 main components. So again, that trend, that seasonality, and that remainder. Right now, what I have written here, obviously this is the additive model because I'm adding all those components together, but it could also be the multiplicative model where I have y sub t is equal to that trend at time t times the seasonality at t times the remainder at t. So we want to decompose that. And then what we want to really focus on is that remainder now. Is the remainder really white noise? And if it's really white noise, then again, we treat it just like a coin flip. One thing is independent of the other, so there is no memory that is being carried along. So we don't need to muddle it any further. If it's just white noise, done. Perfect. But if there is a hidden pattern, if that memory persists over different periods of time, we need to be able to understand and capture that in a model in itself so we can combine these two things together. And like I said, if that pattern does in fact exist, we'll model it right now, and there's other techniques to being able to do it, but the ones we're going to be focusing on is the autoregressive, the moving average, or combining them, the autoregressive moving average models. Again, this is all done on that remainder R sub t. So once we are done and we want to be able to forecast new values, well, what do? I want to say forecast h steps into the future. So I'm going to do t plus h, and again, I have my y hat. So how am I going to do that? Well, I'm going to, again, approximate what the trend is going to be. So what is the trend at that t plus h time? What is the seasonality of that t plus h time? And now, if there is any hidden memory in there, does it carry over all the way up to time t plus h? If so, let's account for that. All right, so we're going to diagnose the residual structure, again, with the ACF, so the autocorrelation function or the partial autocorrelation function. We're going to choose which model we're dealing with. So again, autoregressive moving average, or combining the two, the autoregressive moving average models for different orders, and we'll talk about that as well. Basically, the orders is, again, how long things are going to persist for. We're going to fit these models inside of R, because we've been using R for absolutely everything, and then produce decision-ready forecasts. So once we have everything else, which we kind of already know how to be able to do for the trend, the seasonality, now which is that remainder part of things. All right, so let's get into a little bit of the background of this. This is kind of be the theory part of things. I'm going to try not to go into too much great of detail on this, but again, just a general idea of what we're doing is still important to your general understanding of everything. All right, so kind of our background here. First, let's define a time series, because we've only really kind of talked about this in generality, but let's define this more formally. So a time series is a collection of random variables, so we should remember that from our first SAC course. That could be 2601, 2507, so on and so forth. We were dealing with random variables beforehand, so now we're dealing with a collection of them. So I'll define that collection, or specify what we're talking about in terms of x sub t in the curly brackets, meaning we're dealing with a collection of them. So this is going to be indexed on time, so that's our sub t is based upon time. We usually omit the curly braces when we refer to a time series, because it's kind of understood that we mean this as a time series. If you see the curly brackets x sub t or just x sub t, we're talking about exactly the same thing. So we do this when there's no confusion overall. All right, so what does a time series, a collection of random variables, actually mean? Well, think of it this way. Before tomorrow happens, tomorrow's revenue is an unknown number. Now, it's not fixed. Many values are in fact possible, each with their own probability. Well, that's a random variable. So again, we're trying to measure what's going to happen tomorrow. There is a smattering of different values that it could take, each one with its own probability. So it would be nice to know what probability distribution that we were in fact using. Is this a Poisson distribution? If so, awesome. I could then go, well, what's the average of things happening if I knew something about it? And if I wanted to know what's the probability of a specific value, I can do something along those lines for the next day. Again, assuming I know that distribution. We'll talk about that in a second. That's going to be a big assumption right there. But again, it has that possibility of there is a smattering of different values that it could potentially take. And it's going to take one tomorrow. We just don't know which one it's going to take. So that's a random variable. A time series is just one such random variable at each point in time, again, indexed at time t. So if I'm talking about revenue, x sub t is just the revenue on day t. So why does this matter, this idea of random variables, when we're talking about it in a business sort of context? Well, again, if it's a random variable, and thinking back to how we talked about random variables, there was an expected value, the mean of it all. Well, this would be our expected revenue if we're modeling this as the revenue for time t. There's also the variance that happens inside of a random variable. We can think of this as the risk. How much risk is involved? Is there a large variance, meaning that there is a large potential spread of the data, or is that risk relatively small, that variance relatively small, so we have a general smaller window of what this could in fact be? And of course, then there's the relationship between these random variables, that autocorrelation or that memory across different days, different legs overall. So this is our sort of business context. So again, expected value could be our revenue or expected revenue. That's our mean. The risk is the variance, and the memory is that autocorrelation. So forecasting is about using what we know today to say something about the distribution of tomorrow's random variable. So kind of a starter example here. If we're talking about just a single random variable, it could be just a single day. So tomorrow's orders for Shopko. We might believe that that random variable follows a Poisson distribution with, we'll say, an average of 40. So our lambda is equal to 40. Well, if we knew this, we know the formula for probabilities for a Poisson distribution when we know what lambda is, so we can compute the chances of, well, what is the chance we're going to get 35 orders? What's the chances we're going to get 36 orders? What's the chance we're going to get all the way up to 50 orders for that given day? Again, that's assuming we know something about the distribution. In this case, we're assuming it's a Poisson distribution. Now, in terms of a time series, we repeat this general idea, except we're repeating it every single day. So X1 is the orders on Monday, X2 is the orders on Tuesday, X3 would be Wednesday, so on and so forth. Now, if we assume independence and the same lambda, and if it all follows a Poisson distribution, if each one of those different days follows a Poisson distribution, again with the same average, then we can simply say that X sub t, the distribution, or the time series process, follows a Poisson distribution with lambda or an average of 40. And each day is independent. Okay, if we're talking about independent, we're talking about there is no memory being carried over from time to time. Each one is just completely independent of the other. But again, this is rare in business. There is memory that is carried over from period to period. We just need to be able to capture that. So a collection of random variables is generally referred to as a stochastic process. And if we index this over a period of time, this stochastic process just becomes a time series. Now, because each time period is its own technically random variable, this X sub t, each one could have its own distribution. So one could follow a Poisson distribution with a lambda of 40. One could follow, again, maybe it's still a Poisson distribution with a lambda of 20. Thus, it's since they are their own random variable, they have their own parameters, so their own means, their own variance. So we can think of the random variable x sub t as having a mean, a population mean of mu x sub t, of a variance of sigma squared x sub t, and we can talk about the covariance. Again, what is the relationship between any two of those random variables? So this could be the covariance between x, we'll say t1 and xt2. Of course, we don't really talk about covariance. We typically talk about correlation because this is then a measure between -1 and +1, testing the linearity or the strength of the relationship between the two. So this is our rho at t1, xt2. So the covariance and correlation between two random variables in the same time series, this is what's called an covariance or autocorrelation. So because it's measuring the same thing just at different periods of time, it's autocorrelation or autocovariance. So a couple of things to note there. If we're talking about two time periods which are not the same, so t1 is not equal to t2, it may follow, but not necessarily. So these two averages for the random variables, so at two different time periods, they could have two different means, or they could have the same mean. Their standard deviation could be the same, or it could be different. There's no guarantee. But what is true, if we're talking about the same time period, so if t1 is equal to time 2, then the correlation is always going to be 1. So if we're talking about what is the relationship at lag 0, that's exactly what we're talking about. We're talking about two time periods which are exactly the same. What is the relationship? Well, we're talking about the same thing. It's going to move in exactly the same way. So it's a perfect relationship. It's always going to be 1. But we want to know, well, what happens at lag 1? So a jump of, say, 1 month, or lag 2, a jump of 2 months. How are these random variables moving at the same time? How much memory is carried along? If what happened now is going to affect what's happening 2 months ago, we need to take this into consideration. Definition here. A realization of a time series x sub t is a set of specific outcomes of a random process. This is how we kind of started talking about a time series. We had a time series, we just had values over a period of time. This is what's known as a realization of a time series. So again, each one of our time periods is a random variable. We don't know what's going to spit out, but we know it's going to follow a specific distribution. So think of this as a function. If we hit that time period, out comes a value. We go to the next period, we hit that random variable, out comes a value. We don't know what value is going to come out, but a value is going to come out following its specific distribution. So if we did that, we banged on each of those random variables, a value would come out. That is a realization of a specific time series. And that's, again, what we would normally get is just one single realization of this. But if we knew something about this time series, we were trying to model it, well, we could actually go and hit every single random variable multiple times. So we could have multiple realizations of a time series. Again, this is not typically what we get in practice. What we get in practice is a single realization, and we'll talk about where that becomes problematic, but that's the general idea here. So if we have a collection of these realizations, this is what's known, or the collection of all possible realizations, this is what's known as an ensemble. Now, why is that useful to us? Well, if I'm trying to approximate what the mean and the variance of a random variable is going to be, if I don't know what that distribution is and I want to, again, approximate that, it would be nice if I had more than one value for that random variable. So if my x sub t at time period 1, I just had a single value for that, I could calculate or approximate what the mean is going to be, and the only thing I could do is simply say, I'm going to take this value because it's the only value I know. This is my average. It's the only thing I know. What is the variance? I don't know. I've only got one value in there. I couldn't tell you what the variance is. But if I was able to hit that random variable twice, out comes 2 values. Well, I could take the average of that and I could talk about the variance. Again, it's going to be very limited. I only have 2 values in there. If I could hit it 100 times, have 100 of these values that come out following this distribution, again, I would have a better approximation as to what the center of it's going to be. I'd have a better approximation as what the variance is going to be. The more values, the better the estimate is going to be. But again, the issue is typically we've only been able to hit each random variable once, and I only have one value for each. So how do we talk about the mean, and how do we talk about the autocovariance of our model if I only have one value for each? Well, this is kind of where we're going to not cheat a little bit, but we're going to have to redefine things slightly or take a simplistic look at this. All right, so the mean and the variance of a time series is, we refer to this as a mean function and an autocovariance function because all of this is done through the variable of time. So we talk about the mean function of a time series as mu sub t, which is just the expected value of that random variable at time t. So in general, it's a function of time. Now, autocovariance, same idea. The covariance between two random variables is just the expected value of the random variable minus its center. And again, we multiply the two together, same as we done the calculations beforehand. So we approximated these things back when we were dealing in Stat 2601 under the 2507. But again, now we're talking about this in terms of a time series. But the math is going to be basically the same in this regards. All right, so the autocovariance measures the linear dependency between 2 points in time, and this is going to be our x sub t, s sub, or x sub s, x sub t. So as we said, if we are talking about a lag of 0, we're talking about the same time period. So if S is equal to T, then we're talking about just simply the variance of the time series. We're just measuring one thing in itself. The autocovariance, again, is just at two different points in time. Calculation is still exactly the same. But again, we don't really want the covariance of this. We want correlation because I want a value that I could easily interpret between -1 and +1. So I just need to divide out by the standard deviation of each one of these. So same as we did this beforehand, if I'm looking for the covariance between two time periods, this is just what is the correlation between the two, or covariance between the two, and then we're dividing out by the standard deviation of each one. Okay. And again, I've talked about lag, but it just refers to the different time periods between observations. So if we're talking about a positive serial correlation, so correlation coefficients greater than 0, this indicates that the variable is high or low at certain points in time, and it's more likely to be high or low at subsequent points in the same time period. So if we have a strong correlation at lag 1, so the relationship of what happens the previous month to the next month, there is a strong indication of this that memory carries along, then again, we're going to have a strong correlation. This could be a positive, this could be a negative, so if one goes up, one could go down. If they're both going up, if they're both going down, again, there is going to be a strong relation. If that correlation is just 0, then there is no memory that is being passed along there. Okay, so we've said that each one of these is a random variable, and it would be nice to try and measure the mean and the variance of each one of those random variables. But if we don't know anything about them and we only have one value, how do I approximate this? So this is kind of where the cheating comes into play, or putting a very specific set of requirements on this comes into play. And this is where the idea of stationary comes in. So a stationary time series is one whose properties do not depend on the time in which the series is observed. So if I'm talking about the variance doesn't change over a period of time. The mean, it doesn't change over a period of time. If I calculate it at a time t, or if I calculate it at time s, I'm going to get exactly the same thing. Same with the spread of the data, that variance, I'm going to get it exactly the same. So it's not dependent on time. So if I'm talking about a time series with trend or seasonality, obviously this is not going to be stationary because it's very much dependent on that period of time. Trend is going to be increasing or decreasing, potentially. So if we're talking about averages, that average could be increasing or decreasing depending on where we are in a specific point in time. In terms of seasonality, different seasons, there might be a much wider variability of what could potentially happen there. So again, dependent on time. So automatically, if you have seasonality or trend, gone. Which is why when we're talking about the decomposition of these and looking at the remainder, well, we've already taken out the trend. We've already taken out that seasonality. So hopefully what we have left is something that is in fact stationary. So white noise, we can think of white noise as independent coin flips. Again, no memory being carried along. So white noise is in fact stationary. There's no trend, there is no seasonality to it. Also, there's no memory of anything being carried along. Now, memory, again, doesn't automatically kick things out, but again, if there's trend or seasonality, yeah, that's automatically gone. So if we're talking about white noise, it is in fact stationary. So it doesn't matter when you observe it. If we're talking about the mean, we're talking about the variance, and it's always going to be the same. So in general, a stationary time series will have no predictable patterns in the long term. Now, when we were talking about decomposition of a time series in STAT 2601, we did talk about the fourth component to this, which is the cyclic component to it. So this is repeating patterns, but it's not a seasonal repeating pattern. So this is going to be something that repeats, every 2-3 years. This is kind of like the business cycle of things. Now, we could have this repetition go 2 years. We could have it go 3 years. Again, in terms of the modeling of it, this is modeled through really the trend overall. So if there is a cyclic structure, this actually does not break the stationary component. But if we're talking about trend and seasonality, those do break the seasonal component to it. So kind of note that in most time series encountered, again, we only have that single realization available to us. So if I'm looking to make this meaningful analysis, stationary time series kind of gives us a way of being able to cheat a little bit. So what I mean by this is if we're treating the time series or the realization of a time series as something that is stationary, so it has a constant mean and has a constant variance. So let's kind of just write this down. So if I have an x1, x2, all the way up to xn, and I had some values for this, 1, 5, 10. And again, I was trying to figure out, well, what is the mean and the variance for the first one? What's the mean and variance for the second one? What's the mean and variance for the nth one? Again, I'm not going to be able to do this because I only have that one value. But across the entire time series here, if there was a constant mean and a constant variance, we can stop for a second and go, wait a second. Let's treat all of these observations like they're coming from a single random variable. So the same distribution, the same mean, the same variance. So now instead of just one observation for each, I'm considering this as I have one random variable and I have n observations. And now with n observations, I can kind of cheat a little bit and calculate, well, what is the mean of these n observations? And I can also talk about, well, what is the relationship in the different lags about this? We'll get to that in just 2 seconds, how we approximate that. So there is weak stationary, there is strong stationary. We're not really going to define strong stationary because it's not really used in practice. Weak stationary is what we stick with. And with weak stationary, the conditions that need to be met, well, there's 3. There's really only 2 that need to be met. We automatically get the third is there needs to be a constant mean and a constant autocovariance. So again, that relationship saying it doesn't matter at different times. We're always going to get the for the autocovariance, it's dependent on the space in between, so on the lag, but not on a specific period in time. There we go. So if that is true, if we have autocovariance, it's true across all lags. At lag 0 is the variance, so we automatically get constant variance. So if we have constant autocorrelation, we have constant variance. So really we only need the 2 conditions. The third one is given if we have the 2. So if we do have something that is in fact stationary, then we can estimate the autocovariance function and the autocorrelation function. So how do we do that? Again, assuming that everything is coming from the same distribution. So instead of having just one point, we have these n points for each over an n period of time. Then I can do the calculation as follows. I can talk about the covariance between things at different lags. So the autocovariance function, we can approximate it using this C sub k as I'm going to take observation at time t. I'm going to subtract the estimate for the center of my distribution. So if I have n points, I'm going to find out, well, what is the center of this by just adding them all up and dividing by n. So I can approximate what that center is going to be. So I can take my point at time t minus the center. I can take a point at different lags, so k units or k jumps into the future, minus that center. I multiply them together, and I do this up until I can't do a calculation anymore, and then I divide by n. So if I have x1, x2, x3, x4, x5, all the way up to xn, to do c sub 1, what I'm doing is I'm starting with the first value and the second value and saying, okay, let's take the first one minus the center. Let's take the second one minus the center, multiply these together, and then I'm going to jump over one spot. Now I'm going to do x sub 2, x sub 3. I'm going to take these values subtracted from the approximation of the center, multiply them together, and then I'm going to move on. I'm going to do x3 and x4. And I'm going to keep doing this. I'm going to keep doing this one or k jumps in period of time all the way up until I get to an xn minus 1 xn. And then again, I subtract from the center, I multiply these things together, I add up all of these products, and then I divide by n in the end. So I'm going to do this for a lag of 0, which is just the variance, lag of 1, covariance of lag 1, k is 2 jumps ahead, so on and so forth. This is how we approximate it. So the number of time steps between variables, again, is known as the lag, and that the autocovariance at lag 0, C0, is just the variance calculated with a denominator of n. So also kind of note here, we're always keeping the denominator n, even though we're not going to have n calculations on the top. So this could be problematic, or we could think of this as being problematic, but in reality, it's not going to be that much of an issue. There's other functions where we're not specifically dividing by n, but again, we kind of make this work in the next calculation. So how many calculations are we actually dealing with? Well, it depends on the leg. So n minus k is the number of terms that we're going to have on the top, but we're always dividing by n. So where do we fix this? We fix this in this last little bit when we're talking about the correlation. So r sub k, this is trying to approximate rho sub k, so the correlation between 2 points in time. How do we do that? Well, I'm simply taking what is our approximation at leg k, what is our approximation at leg 0, and dividing these two, finding that ratio. This is going to get us our rho sub k, or our approximation for what is the covariance at leg k. All right, so how do we do this inside of R? We're just going to use the ACF function. So ACF with my time series X, I put that thing through. If I want all of these autocorrelations, then all I'm going to do is simply do $ once I generate this. $, so the specific part of the list that I'm going to be referencing is the ACF. That's going to give me the vector with all of the different legs in there. If I wanted a very specific one, if I wanted at leg k, well then how do I reference this inside of my vector? I have to go k plus 1. Why is that? Because we always start at leg 0. So at leg 0, if I were to try and put in ACF, so $ACF at leg 0, what's the problem of this is we don't index vectors starting at 0. We always start at 1. So if I were to say, well, what's in position 0, it's going to throw back an error. There's nothing there. So I have to start at position 1, which is why we go k plus 1. So at leg 0, start at 1. At leg 2, I go to, if my leg of 0, I start in position 1. A leg of 1, I go to position 2. A leg of 2, I go to position 3, so on and so forth from there. Now we saw the ACF beforehand because it produced a graph for us. Let's kind of define that graph here for a second. So this is the correlogram. So a correlogram is a graph used to interpret a set of autocorrelation coefficients, so that's r sub k, against k, again, that lag of it. So what is this graph? This graph on our y-axis represents r sub k, or the approximation of the covariance, and then k is our x-axis, so it's just done over the different periods of time. So a correlogram is often used for visual inspection. Some general advice when we interpret this is as follows. So if we're dealing with a random time series, so a time series is completely random, no trend, no seasonality, then there should be no relationship or no memory being carried along. So if we're talking about the autocorrelation, again, no memory, r sub k should be approximately 0. This is going to be true for non-zero values, because again, if I'm talking about what is the relationship at leg 0, I'm talking about what is the relationship between a variable and itself, that's always going to be 1. But if I'm talking about what is the memory between now and another time period, well, again, if it's completely random at this point in time, so we've removed all of the important aspects of it, then there is no memory that is being carried along. So when I build that correlogram, everything should be close to 0 at the different legs other than 0. Now, if a time series contains trend, then what we should be seeing is there is going to be a steady decrease in at different lags. So we're going to see things, eventually that memory that's being passed through will eventually fade, but it's going to, again, we're going to see a decrease. So there's going to be a strong relationship early on, or it could last for a long period of time, but again, that memory will fade over a period. And if there's fluctuations in the correlogram, usually this is indicating for us that there's seasonal fluctuations going on as well. Again, this is all done with the ACF function. All right, so let's kind of go through a quick example here inside of R. Let's play around with all this, because this was a lot. All right, so what do we need? Let's bring in the different libraries. So you should have these all installed by now. If not, you have to do the install.packages function. Since we've already done that, I'm just calling these from the library. So on line 5 and line 6, I'm just going to call forecast and ggplot2. So load these from the library. There we go. Good to go now. So I'm going to generate some random data here. So let's set a seed. So the seed is going to be 2025. Now I want to create a time series. So the first thing that I'm going to do is I'm going to create a variable called dates. This is going to be a sequence starting at 2017, January 1st. We're going to build this sequence by months, and we're going to do this for a total of 96 months. So I've created a vector called dates, and if we just move this down here, we can see I have that variable dates starting at 2017, the first day of the first month, going to the next month, so February 1st, and so on and so forth. There we go. Thought I was about to sneeze there for a second. Now I'm going to go n, the number of time periods that we have. That's just going to be the length of it. It's going to be 96 because there's 96 months. And I'm going to build a time vector that's just going from period 1 all the way up to period n. There we go. So what we're going to do here, again, we're going to build the time series. So we know inherently what is happening. Now, again, when we get a time series or a realization of a time series, we're not going to know all of this background information. So we're going to try and decompose it into its specific points or specific parts. So here we're going to create the time series so we know it contains all of this, and then we can kind of see, well, if we break it down, how close are we to these types of approximations? All right, so what's the trend? The trend is going to have an intercept of 600, and it's going to have a slope of 4. So I built my trend vector. Now I'm going to build a seasonal vector. So I'm going to say, starting in January all the way up to December, it's going to follow the following pattern. So I'm going to see a decrease, so minus 80 in January. February is going to see a decrease, so minus 40, so on and so forth. But then about halfway through the year, we're going to start seeing an increase. There's going to be some decreases in here. But then towards the end, so like the October, November, December, we're going to see increases. So I have an increase of 50, 120, and 160. Let's suppose these are units. This could be revenue overall. But we're seeing this seasonal fluctuation. So I'm going to create a seasonal vector following this. Now I'm going to repeat this vector, and I'm going to do it for a total of 96 observations. So it's just going to keep repeating. So if these are my 12 months, I'm going to repeat this until I have 96 months in total. So I have a seasonal vector, again, starting at 80, going all the way up to 160. That's 1 year. Then it repeats itself, 80 all the way up to 160. So it's going to keep doing this over and over and over again. All right, so let's also create some memory that's going on here. So potential promos that are happening. So let's create a vector. And this vector is just going to say, I'm going to have a promo for all 96 months. I'm just going to set this equal to 0 for now. Now, I'm going to pick specific dates in time. So we'll say, whoops. There we go. We'll say at time period 2019 on the 8th month on the first day, we're going to run a promo. So we're going to see an increase of say 60 units or 60 units in revenue overall. On 2021 on the 4th month first day, we're going to see an increase of 50, so on and so forth. So I'm going to do this for a total of 4 different promos. So my vector is going to be of size 96. It's all going to be zeros except for those 4 specific days. Now let's say there was a supply issue. So I'm going to create a shock vector, which again is going to be of size 96. All the values are going to be 0. Now there's going to be some decreases here at very specific points in time. So let's say in 2020, in month 4 and month 5, there's both going to be some issue in here. This could have been, well, 2020, what are we talking about? That was COVID periods of time. So we'll say in the first really 2 months when everything shut down, major disruptions that happened in there. So we'll see a minus 120 and minus 120 for both the 4th and 5th month. All right. And now let's put a little bit of memory inside of here. We're not going to really talk about all of this, but this is, because we'll build this all in the next little lesson here. But this is where we're going to follow a autoregressive moving average model. So this is where the remainder is going to have some level of memory. We're going to talk about explicitly what this all means, but we're going to get to that point in time, just not yet. So just think of this now as I'm creating something with memory in it. So when I put now the revenue together, so my time series, I have the trend, I have the seasonality, I have these promos that are in here, I have this shock that's happening, and I have that remainder that's carrying memory. So all of these are vectors of size 96. So putting them all together, additive gives us an additive model, and I'm going to call this revenue. So if I look at rev, oops, revenue. Why can't I spell? There we go. Put this to the screen. So I have the 96 observations. So this is the revenue of every single one of those months. So we could plot this. There we go. We'll just plot it as a time, or using the plot function. So this is kind of what we see. Is there a seasonal aspect of it? Well, there could be a seasonal aspect. There seems to be some ups and downs. There's definitely a trend aspect to this. But let's try and decompose this. Now, we can... Well, actually, I want to change this first. Let's get rid of this plot part here. Let's change this into a time series. Right now, this is just a vector, so I can use the TS function, putting in this vector, and I'm just going to say this is going to start in 2017, the first month with a frequency of 12. So rev underscore TS, this is now a time series. So let's plot this. There we go. Now that looks a little bit better instead of dots. So we'll say this is Shopko's monthly revenue starting at 2017 for 96 months. All right, so if I want to be able to decompose this, one of the things I could use, we didn't talk about this last time, we did this manually. One of the things that we could do is the STL function, putting this in, breaking the window down into periodic. So I'm going to break this into its different components. So fit STL, break this down. It's a list of 8 things. So let's open this up for a second. So we have the original time series in here. We have different weights, but what else do we have? We have oh, it's inside the time series. And so we have the original time series, but we also have this broken down into its 2 main components. So I can auto plot this fit STL underscore STL, and this is going to break things down in the same way we had things before. So it has the original data that we have. So this is our time series over the different periods of time. It's broken down into the trend component. It's broken down into the seasonal component, and it's broken down into the remainder component of this. So I can pull each one of these components just using the different function calls. So I can do trend cycle, seasonal, and remainder function calls from this fit underscore STL. So this is going to pull the trend component, this is going to pull the seasonal component, this is going to pull the remainder component. I'm going to store this in variable names TT, ST, and RT. So I have my trend component, I have my seasonal component, and now I have my remainder component. Okay. So at this point in time, and this is kind of where we left things last time, we decomposed it down into these 3 main components there, so the original time series and the 3 parts of it. Now the question that we want to be able to ask, is there still information that can be tracked in the remainder? Is there memory in there that we need to be able to capture? So this is where we can use the ACF function for this. So let's just do the ACF function on the remainder. And I'll do the PACF as well. And let's make this a little bit bigger. So the ACF of the remainder, so we're asking the question, is there memory? So at leg 0, we don't really care about things at leg 0, because when we're asking what is the relationship between something and itself, it's always going to be 1. But what happens, again, this is in months, so what happens if I jump to lag 1? So I'm going to jump 1 step into the future. This tells me that there is a correlation of, it's about 0.5. Okay, so this is substantial. So memory is being carried over. So how these 2 points in time move are going to be strongly related to one another, positively. So if one increases, the other increases. If one decreases, the other is going to decrease. So taking advantage of this would be a key point. Well, what about 2 jumps into the future? Well, 2 jumps into the future, we don't really see much that's going on here. So when we're in between these blue lines, these bounds, what this basically means is this is the equivalent to 0. That we expect there to be some level of noise inside of there. But if it's not statistically significant, so if it's not outside of these bounds, so think of this as we're doing a hypothesis test. That hypothesis test is asking, is R sub k equal, or is rho equal to 0? So at lag k, is the true population parameter equal to 0, or is there something statistically there? So we could approximate this, we could get a value, but in terms of is this true for the population parameter, this is kind of where that hypothesis test comes into play. So if we fall outside of these blue bounds, then we have things that are statistically significant. If we fall within, then we have things that are not statistically significant. So at time period 2, so memory between 2 months, we see that there is a little something here, but we're expecting some random noise overall. It's not outside of the blue bound, so it's not really helpful. At 3 months, okay, we're seeing something. 4 months, we're seeing something. 5 months, we're seeing something. 6 months, we're seeing something, so on and so forth. There does come points in time where we're not seeing something. So we see a decrease. We see these ups and downs patterns. So again, based upon the breakdown of this, we can expect that there is something that is being carried over from time period to time period. What about that partial autocorrelation? So if we take out what we already know from previous, so this is not starting at lag 0, this starts at lag 1. So there is still information that's happening here. What happens if we go to lag 2? At lag 2, again, there's still some information that's being happened here once we remove that little bit from the first. Where is this? We'll explain where this is helping us in a little bit. We don't really need this right now. What we really need is the ACF to tell us, is there memory being carried over? And at this point, yes, there is memory being carried over. This is not just random noise. If this was random noise, what I would see is after lag 0, so lag 1 and above, everything would be between those blue lines. That means when we did the calculations to estimate it, something was there, but it's not statistically significant. Here we have values that are statistically significant, which means memory is being passed along. So if I were to model this, and we'll talk about more of this when we get to the next part of the lesson, of the second part of this. So I'm going to try and model this right away. I'm not going to explain what this is doing because we'll explain that when we get to this point in time. But here I'm going to try and model what that remainder is going to be. So I'm going to do an autoregressive moving average model. It's going to take a second to build up here, but this is trying to model that remainder of what is left. And then hopefully, once I've modeled this remainder of what is left, the residuals, once I've figured out what that pattern is going to be, the residuals of this, so again, we're not talking about the trend, we're not talking about seasonality. I have the R sub t, this remainder. I'm just trying to model the memory here. So once I've modeled the memory, there's still going to be a residual aspect of it. So what the model produces versus what the true value is going to be. What I'm looking at the end of that, those residuals, those errors of what's happening here, that should be white noise. So now if I run ACF on those residuals, notice at lag 0, a correlation at 1, that's exactly what we want, but everything afterwards is within those blue bounds. So there is something there, but statistically it's irrelevant. So what this means is that random component, that memory that was left overall, we were able to model that, and the noise that's left over, once we've been able to model that, is just noise in the end. We've successfully isolated the different patterns in here. So now I can approximate the memory, I can approximate the trend, and I can approximate the seasonal component to this. So again, this is all done using the ACF function. So what we're going to do in the next little bit here, so in the next lesson, because we're already at 53 minutes, so we'll end this one here and we'll talk about the different models because that's all that's really left on this. We have the moving average, the autoregressive, and then combining the two, the autoregressive moving average models. We'll talk about those briefly in the next video, which probably won't be all that long, but I don't want to do a massively long video here. And then that'll complete everything. So yeah, we'll end it there. If there's any questions, comments, concerns, we'll see you the next time.